You know, usually when we talk about a medical diagnosis, there's this expectation of absolute, like, engineering level precision. You fall, you break your arm, the X-ray shows that jagged white line, and the doctor just points at the screen and says, there it is, broken.
Right, yeah, it's a very comforting binary. We inherently like things to be visible and, easily categorized.
But then you step into the world of oncology, specifically gastric cancer, and suddenly that clean X-ray machine feels like it's broken. We're looking at a diagnostic landscape that is, honestly, just kind of murky.
Oh, absolutely. It's incredibly complex.
Right. So welcome to the deep dive. I'm so glad you could join us today. We've got a massive stack of data to unpack for you, specifically a groundbreaking study recently published in NPJ Precision Oncology, along with just a mountain of supplementary pathological data.
And it is a fascinating data set to dig into.
It really is. Our mission today is to explore a new deep learning framework designed for gastric cancer. And just to set the stakes for you, gastric cancer is the 5th most common cancer globally, and it is highly lethal. We are looking at a tool that uses artificial intelligence to completely rethink how we predict patient survival and, crucially, what treatments they actually get.
Yeah, and to really appreciate why this framework matters, we have to look at the flaw in how we currently categorize cancer patients.
Okay, let's unpack this. Let's introduce a hypothetical clinical case drawn right from the core problem this paper addresses. Imagine you are an oncologist. You have 2 patients, patient A and patient B. Both are diagnosed with stage 3 gastric cancer.
Right, exactly the same stage.
Yeah. According to the gold standard staging system we use today, the TNM system, which stands for tumor size, lymph node involvement, and metastasis on paper, these 2 patients are identical.
Their TNM staging perfectly mirrors each other.
So following protocol, you give them the exact same aggressive chemotherapy. Patient A responds beautifully. The tumor shrinks, they go into remission. Patient B, however, doesn't respond at all. The treatment just causes toxic side effects, and they tragically pass away within a year.
It's a devastating scenario, and unfortunately, a very real one.
If the cancer is the quote-unquote same stage, why are the outcomes practically opposites?
Well, the discrepancy comes down to a biological reality called tumor heterogeneity.
Tumor heterogeneity.
Yeah, so a tumor is not just a uniform lump of identical, predictable cells. It is a highly chaotic ecosystem. It has its own blood supply, rogue immune cells, necrotic dead zones, and actively mutating regions.
Wow, okay, so it's really an ecosystem.
Exactly, and the TNM system is purely a macroscopic measurement. It tells you how far the cancer has physically spread geographically in the body. But it tells you absolutely nothing about the biological personality of the tumor at a microscopic cellular level.
So TNM is basically looking at the borders of a country, but telling you nothing about the politics or the weather inside.
That is a perfect way to put it. We need to look closer.
And that brings us to the raw material the researchers used. They gathered data from over 3,000 patients. The primary data set is HMU-GC, with over 2,800 patients from Harbin Medical University in China.
Which is a huge cohort.
Huge. And the second is an independent external data set called TCGA-STAD, representing about 355 patients. But they didn't just feed spreadsheets into an AI, they used high-resolution pathological images.
Right, the actual tissue slides.
Yeah. When a patient has a biopsy, that tiny piece of tissue is sliced incredibly thin, placed on a glass slide, and stained using a century-old routine called H&E hematoxylin and eosin.
Yeah, H&E hematoxylin is a dark blue dye that binds specifically to acidic structures, primarily the DNA packed inside the cell nucleus.
Okay, so the blue shows the nucleus.
Right, and eosin is a pink dye that binds to basic structures, like the proteins in the cell cytoplasm. This blue and pink contrasting landscape is what allows a human pathologist to look through a microscope and visually parse the architecture of the tissue.
But for an algorithm to see that pink and blue landscape, those physical glass slides have to be digitized into whole slide images, or WSIs. And these files are staggeringly massive. We are talking multi-gigapixel images.
They are enormous.
A standard 4K television has about 8 million pixels. A single WSI can have billions. So my immediate thought is, if you feed a multi-gigapixel image into an AI, wouldn't you just instantly crash a standard computer? How do you even process that map without losing the microscopic details the AI needs?
That computational bottleneck is a massive hurdle in digital pathology. The researchers solved it through a process called resolution normalization. You simply cannot feed the whole gigapixel image into the network at once. You have to break it down.
Makes sense.
They used an open source tool called CLAM to process these images. First, CLAM identifies where the actual tissue is, entirely ignoring the blank white background of the glass slide.
And it has to deal with real-world messiness, right? Because pathologists literally draw on these slides with marker pens to circle things.
They do. And CLAM acts like a digital squeegee, excluding those pen marks and any physical folds in the tissue where the slice got bunched up.
That's amazing.
Once the usable tissue is isolated, they slice the image into tiny, non-overlapping patches. But here's the critical mechanism. Different hospitals might scan slides at different magnifications, some at 20x, some at 40x.
Oh, right, so the zoom level is different.
Exactly. So to ensure the AI isn't confused by scale, they digitally downsample the higher magnification images. Every single patch fed into the AI ends up as a standardized 512 by 512 pixel square representing the exact same physical area of tissue.
Okay, so if I'm tracking with you, we're basically taking this massive, messy biological landscape, wiping off the literal pen marks and background glass, and chopping it into thousands of identical 512 by 512 pixel squares. The AI is always comparing apples to apples.
Precisely. Apples to apples.
But that brings up a huge question. If a human can't process millions of these tiny squares manually, how does the algorithm actually make sense of them to predict survival?
Well, they engineered a core technology called a weakly supervised transformer.
Okay, let me push back on that phrasing. Weakly supervised sounds terrible when we're talking about life or death medical algorithms. I know in machine learning, strong supervision means a human manually labels everything. So if this is weakly supervised, what is the AI actually doing?
It's a completely counterintuitive term, I know. Strong supervision in this context would mean a human pathologist sitting down and manually drawing circles around every single cancer cell and immune cell across millions of patches to tell the AI exactly what to look at.
Which is impossible.
Right. That is physically impossible at this scale.
So is weak supervision like asking a detective to figure out what makes a certain neighborhood dangerous, but only giving them the overall crime rates of the whole city rather than pointing out the specific criminals?
That is a perfect analogy. We don't hold the AI's hand at the microscopic level. We just hand it the thousands of patches for a single patient, provide the patient's ultimate survival outcome, the crime rate of your analogy, and say, you figure out the visual connection.
That's wild, but how does it even know what a cell is?
To do that effectively, the AI needs a baseline understanding of what it's looking at. They utilized a foundation model called UNI. UNI looks at a single 512 by 512 pixel patch and instantly translates its complex visual features into a 1024-dimensional feature vector.
Okay, wait. Let's ground that math in reality. If I describe an apple, I might use 3 dimensions. Its color is red, its weight is 150 grams, its sweetness is high. What does a 1024-dimensional vector mean for a piece of human tissue?
So instead of sweetness or weight, the UNI model is extracting 124 distinct biological and structural dimensions. It might be measuring the jaggedness of a nucleus membrane, or the exact density of the blue hematoxylin dye, the physical distance between a tumor cell and an adjacent immune cell, or the texture of the connective tissue. It basically converts biology into a massive mathematical fingerprint.
A mathematical fingerprint, I like that. And you mentioned earlier that the overarching architecture here is a transformer. I know transformers from text processing, like how ChatGPT predicts the next word in a sentence based on the words before it. But how does a transformer read an image?
It applies that exact same logic to visuals. It treats each 512 by 512 patch of tissue like a single word, and the entire whole slide image is a paragraph.
Oh, wow.
Yeah, the transformer uses an attention mechanism to understand the context of how these words are arranged. It learns that a specific type of aggressive tumor cell patch only matters if it's sitting directly next to a patch showing suppressed immune cells. It learns the spatial grammar of the cancer.
I see. But the math still presents a logistical nightmare. Patient A might have a massive tumor resulting in 10,000 image patches. Patient B might have a small tumor resulting in only 2,000 patches. Deep learning algorithms process data in rigid matrices. How do you feed differing numbers of patches into the same neural network without breaking it?
You implement a multi-patient batch padding strategy. Let's say the maximum number of patches any patient has in the current processing batch is 10,000.
Okay.
For patient B, who only has 2,000 actual tissue patches, the system literally adds 8,000 blank patches, pure zeros, to pad out the matrix so it matches the size of patient A.
But wait, if I'm the AI and you just handed me 8,000 blank images, wouldn't I wildly miscalculate and think this patient is 80% healthy because there's no cancer in those squares?
That would happen, absolutely, unless you use a binary mask.
A binary mask.
Yeah. The researchers apply a digital blindfold over all those padded zeros. It sends a strict instruction to the transformer's attention mechanism. Ignore anything in these padded zones. Give them zero mathematical weight. This elegant trick allows the system to process vastly different sized tumors simultaneously in parallel, dramatically speeding up computation without corrupting the learning process.
So the AI is looking at the real patches, extracting 124 dimensions of biological data, understanding the spatial grammar, and trying to predict survival. But how does the AI score itself during training to know if it's getting better or worse?
It uses a dual scoring system called a joint survival loss function.
Okay, break that down for me.
Sure. The first component is negative log likelihood, or NLL. NLL evaluates how accurately the model captures the temporal survival distribution. It's strictly about getting the timeline right. Did it accurately predict the probability of survival at year 1, year 2, and year 3?
Okay, so NLL is the stopwatch.
Yes. And the second component is the ranking loss. This is where it gets highly sophisticated. Ranking loss explicitly penalizes the AI if it messes up the relative order of the patients.
Let me guess. If patient A lived for 5 years and patient B died after 1 year, but the AI assigns a higher overall risk score to patient A, the ranking loss acts like an electric shock.
Exactly.
It forces the network to adjust its internal weights because it ordered them wrong, regardless of the exact timeline.
You've got it. By combining NLL for strip time accuracy and ranking loss for relative ordering, the AI becomes incredibly sharp at stratifying patients into distinct risk categories.
Okay, this is a lot of complex engineering. Let's take a quick breather and just do a rapid 5-minute bulleted recap for you listening, summarizing the first half of what we've covered.
Good idea.
Bullet 1. TNM staging isn't enough because it misses tumor heterogeneity. 2, WSIs are massive digitized tissue maps, and we clean them up and chop them into identical patches. And 3, the transformer AI looks at these maps in standardized patches to learn survival patterns using weak supervision, so without needing human hand-holding.
That pretty much covers the engine.
So we have this massive digital engine processing millions of patches, constantly correcting itself. What does it actually spit out at the end? What is the tangible result for the doctor?
The output is a single metric, TPRS, or the transformer-based pathological risk score. Right. To make this score actionable, the researchers established a threshold. By analyzing the training data, they found the 65th percentile was the optimal cutoff point.
So what does that cutoff mean for a patient?
If your TPRS is below the 65th percentile, you are classified as low risk. Above that, you are high risk. And the survival curves between these two groups diverge dramatically.
But a score that just tells you bad news isn't revolutionary. You mentioned earlier this changes what treatments patients get. Let's revisit our clinical case. Patient A and patient B, both stage 3 according to the old TNM system.
Here's where it gets really interesting.
Nice.
This is where TPRS changes the game. The study proved that for stage 3 patients, having a high TPRS score unlocked a massive, statistically significant survival benefit from receiving specific adjuvant chemotherapies.
Adjuvant chemotherapy meaning chemo administered after the main surgery to mop up any microscopic cancer cells left behind. They specifically highlight drug regimens like SOX and XELOX, which use platinum-based drugs and fluorosil derivatives. But why? Why do these specific drugs work miracles for high TPRS patients, but not the low TPRS patients?
Well, it comes back to the tumor's biological personality. A high TPRS indicates highly chaotic, aggressive, and fast-dividing tumor environment.
Right.
Platinum-based drugs physically bind to DNA, creating crosslinks that prevent the DNA from unzipping, which aggressively dividing cells absolutely must do to replicate.
Yeah.
Fluorosil derivatives interfere directly with the building blocks of RNA and DNA. These drugs are essentially cluster bombs for rapidly dividing cells.
I see. So the AI is flagging the precise biological profile of a tumor that is dividing so recklessly that it makes itself deeply vulnerable to DNA-binding drugs.
Exactly.
While the low TPRS tumor is dividing slower or differently, so hitting the patient with those highly toxic platinum drugs just poisons them without killing the cancer. TPRS can literally tell an oncologist to spare a patient from toxic side effects if the biology doesn't warrant it.
That is the ultimate goal of precision medicine, and the statistical validation for this is robust. They measured performance using a C-index.
What's a C-index?
It evaluates how perfectly the model predicts the order of survival times. The TPRS achieved a C-index of around 0.765 internally.
Wow.
And it held up beautifully on the entirely separate TCGA stat external cohort.
To contextualize 0.765 for you listeners in complex biological survival prediction, anything over zero point 0.7 is considered a very strong model. But did they test it against the current gold standard? Does TPRS actually beat the TNM system?
They ran it through a multivariate Cox regression analysis.
So that's basically a statistical bouncer. It looks at every factor, age, gender, TNM stage, and TPRS, and tests if TPRS still matters when all the other variables are already accounted for.
Exactly that. The Cox regression proved TPRS is an independent prognostic factor. Even when you know the patient's exact TNM stage, TPRS provides critical predictive power that the geographic spread of the cancer completely misses.
So if I'm tracking the journey here, we take cheap glass slides, digitize them, standardize the patches, feed them through an attention-based transformer that learns from crime rate-style weak supervision, and out pops a TPRS score that accurately dictates chemotherapy.
That's the pipeline.
But if I'm the doctor and an algorithm tells me to give a patient a highly toxic platinum drug, I'm not just going to blindly obey. I need to know why the AI made that choice. You cannot have a black box dictating medical treatments.
The researchers knew that interpretability was non-negotiable. They had to prove the AI wasn't just hallucinating patterns or obsessing over the color of the background glass.
To understand how they open this black box, I want you listening to keep a simple mnemonic in mind. GCPT, gene, cellular feature, TPRS.
GCT. I like that.
Yeah. The researchers worked backwards through this GCT chain, starting from the AI's final score.
Step one was visualizing the AI's thought process. Because the transformer uses that attention mechanism we discussed, the researchers could command it to output heat maps. This literally creates a visual map highlighting the exact microscopic patches of tissue the AI paid the most mathematical attention to when generating a high TPRS score.
It's like eye-tracking software for the algorithm.
Precisely.
So they look at these hot patches. What exactly was the AI staring at?
What's fascinating here is, to find out, they deployed advanced image segmentation tools. One key tool was HoverNet.
Let's explain the mechanism there. HoverNet is basically an artificial neural network acting like a highly intelligent digital cookie cutter, right?
Yeah.
It isolates the exact shape and boundary of every single cell nucleus, like finding the yolk in a fried egg.
That's the perfect way to visualize it. It segments the nuclei and predicts the cell type based on its morphology. And then they paired that with CyberSort.
CyberSort.
Yes, an analytical tool that deconvolutes bulk data to profile the specific types of immune cells present in the tissue.
Okay, so that gives us the C in our GCT chain cellular features. The AI's heat maps proved it was staring at specific irregular cell shapes, dense clusters of nuclei, and specific spatial relationships between rogue tumor cells and failing immune cells.
Exactly. It was looking at actual biology.
Yeah.
But they took it one step deeper. They linked the C down to the G genes.
How do you go from a picture to genetics?
Because the researchers also had bulk RNA sequencing data for these patients, they could cross-reference the high TPRS scores with genetic expression. They found that patients with high TPRS scores had highly specific molecular pathways, acting up pathways that perfectly matched the physical cellular features the AI was flagging.
Give us a concrete example. What specific genes were driving the shapes the AI saw?
Two heavily implicated genes were OR7A17 and PANX3.
OR7A17 and PANX3. Got it.
These genes are known drivers of tumor metastasis. PANX3, for instance, is deeply involved in forming gap junctions, communication channels between cells, and regulating the pH within the tumor microenvironment.
And pH is massive in oncology. Tumors often create a highly acidic microenvironment. That acidity literally degrades the surrounding healthy tissue matrix, physically clearing a path for the cancer to invade and metastasize.
Exactly.
So if a gene like PANX3 is mutating and driving up that acidity, the physical shapes of the cells and the tissue around them will change?
And that is the brilliance of this framework. The AI knows absolutely nothing about PANX3.
Yeah.
It knows nothing about pH levels. But it visually spotted the architectural chaos and the cellular damage that are the direct physical consequences of those genes acting up.
Wow. So the GCT explanatory chain gene expression alters cellular morphology, which the AI reads to generate the TPRS score, completely shatters the black box.
It has it.
The algorithm isn't guessing, is visually identifying the downstream physical footprint of metastatic genes.
It creates an unbroken line of logic from the invisible molecular level all the way up to patient survival.
That is just incredible. Okay, before we wrap up, let's do a final quick bulleted summary. Bullet 1. TPRS accurately predicts survival and chemotherapy benefits. Bullet 2. It proved effective across multiple distinct patient datasets, proving it's reliable. And bullet 3. The GCT chain proves the AI is looking at real biological phenomena, genes, and cell shapes, not just digital noise.
Perfect summary.
So what does this all mean? As we pull all of this together, what does this actually mean for the future of medicine? This isn't just a marginal improvement in gastric cancer staging. This study is a massive neon blueprint for democratizing precision oncology.
It really is a paradigm shift.
We are taking standard, incredibly cheap, century-old H&E glass slides, and we are extracting a wealth of profound genomic and prognostic data from them. We're doing it without destroying the patient's tissue and without requiring $100,000 genetic sequencing tests for every single person who walks into a clinic.
It makes world-class precision medicine accessible to hospitals that might only have a standard microscope and an internet connection.
And while this study successfully linked the average genetic expression of the tumor to what the AI was seeing, it leaves us with an incredibly provocative thought about where this technology goes next.
Oh, the next frontier is spatial transcriptomic.
Let's talk about that.
Right now, bulk RNA sequencing is like putting the whole tumor in a blender and measuring the average genetics. Spatial transcriptomics allows us to map the exact RNA sequence to the exact individual cell on a slide without blending it up.
So imagine a future where the AI doesn't just look at a patch of tissue and predict an overall survival score. Imagine it flags a single specific cell on the slide.
Right.
And because of spatial transcriptomics, the AI can instantly tell the oncologist the exact genetic mutation driving that specific cell and exactly which microdose of medication will destroy it. It moves from predicting the storm to mapping every single raindrop.
It's going to change everything.
We started this journey by talking about the murky, imprecise waters of oncology and how we missed the clean binary of a broken bone on an X-ray. But perhaps this AI framework is the new X-ray machine. It's peeling back the chaotic layers of tumor heterogeneity to reveal the hidden microscopic architecture of cancer.
It brings precision back to the diagnosis.
I leave you with this final thought. If you were a doctor, would you trust an AI's treatment recommendation more if you could see the exact cells and genes it based its decision on? Think about how this changes the dynamic between human intuition and machine calculation. How soon before the human doctor isn't making the diagnosis, but simply verifying the machine's absolute precision. Thank you so much for joining us on this deep dive. Keep questioning, keep exploring, and we'll see you next time.